Right, let's go to our next examples, still here in lesson 1.2 from Wednesday. So you can see here I've already graphed the piecewise function using values for each arm. Notice I wrote in which values you're supposed to use. Okay, and now we need to answer the question, which is to figure out if the function is continuous at x equals -2. All right, you might wonder, okay, how are we supposed to do that? Well, we've already done part 1, which is to graph it. So part 2, according to our theorem of limits of rational functions, we need to show that the limit as x goes to -2 should be of the function g of x should be equal to g of -2. That's our goal. If we can do that, we can show that the function is continuous. Okay, so first let's figure out if the function exists. Okay, so in order to do that, we need to do the limit as x goes to -2 from the left, figure out that, and the limit as x goes to -2 from the right. And you have to choose the correct functions to use. Okay, so if we're coming in from the left, that means we're using small numbers which are less than -2. If we're coming in from the right, that means we're using big numbers, and we're going to use this function x minus 1. Okay, so if we plug in our values, if I plug in -2 into this function, I should get -1 plus 3, which is 2. And if I plug in -2 into this function, I'll get -3. I can clearly see that the limit as x goes to -2 from the left does not equal the limit as x goes to -2 from the right, so it doesn't exist. And if it doesn't exist, then it's not continuous. So it's not continuous. And then we're done with that problem. Let's take a look at example 9. Let's see if we can find something continuous here. Again, according to our rules, we need to graph it and then use our theorem of limits of rational function. Okay, again, we have a series of restrictions here. For any value at all, we can use this lower arm. And when x is not 4, we use this upper arm. But look at this function. This rational function is pretty large. And I know that you remember your factoring rules, so you know that we could factor and simplify this rational function so that we're really using x plus 4. Okay, so first of all, let's graph x plus 4 on our number line. Intercept will be at 4, slope of 1. And we're going to connect the dots. Of course, in a perfect world, we'd be using a straight edge. And what about the second function? It says when x is 4, that y is 7. And that's here. Okay, so we're going to check and see if this is continuous. So, according to our limit rule, the limit as x goes to 4 of the function f of x should be equal to f of 4. So our limit as x goes to 4 of x plus 4 will give us 4 plus 4, which is 8. And f of 4, that's going to just be 7 per this function to begin with. So these are kind of neat because they're sort of done already. And of course, we can tell that 7 does not equal 8, so the function is not continuous on x equals 4. Let's take a look at our quick check problem here. Quick check problems always make sure that we know what we're doing here. So with this problem, again, we have another piecewise function that we need to graph.